Okay, and then the last topic that we're going to look at here, we'll call this case 2. Case 1 was just the springs. There's 2 different types. We're going to look at pendulums. So remember, a pendulum is another object that also demonstrates simple harmonic motion, but this is only simple harmonic motion, and you'll see that we use this abbreviation all the time, SHM, for small amplitudes. Say less than, some people say less than 10 degrees, less than 15 degrees is pretty good. And so I'll explain what I mean by this in a second here. So we've got a pendulum. We've got a pendulum attached to the ceiling here. This part down here at the bottom of the pendulum, sometimes we call this the bob. Pendulum has got some sort of length, and the bob has some sort of mass. When we're talking about ideal pendulums, we assume that the pendulum itself has no mass. The only mass that we're talking about is at the end. And so with pendulum, what happens is obviously, well, we take the pendulum, we pull it to the side. Here's our equilibrium position, is where it will naturally come to rest. And we pull it to the side by some angle. And just like when we were talking about springs, there was a force causing it to return to its original position. In this case, there is a force causing it to return to its original position. So we've got a restoring force here as well. This one can be a little bit more complicated to think about what this restoring force is. So let's draw a free body diagram again of all the forces that are acting on this pendulum at this moment. Well, really, we've got a force of gravity, and we've got a force of tension. This restoring force here, this is not actually like a real force that is acting on it. Remember, the restoring force here is really just the net force. So really what we want here is we're asking what component of our force is acting in this direction. How much of the force is acting in this direction? And if we kind of redraw our forces here, we can kind of work this out. And we can say, okay, well, we've got the force of gravity is pulling it down. We've got force of tension is acting perpendicular to this restoring force. So really, we can think about this restoring force is really sort of equal to the force of gravity. We've got a triangle here, we've got a right angle triangle, and so we can say it's equal to the force of gravity, but it's equal to just the component pointing in that direction. And this one's a little bit tricky to remember. So most of the time, you can jump straight to this equation here is fine and say that your restoring force is just going to be equal to your force of gravity times sine of theta, sine of your angle. And the reason that we say that this is still a proportional relationship and why it works for small amplitudes is if you look at the graph of sine of theta. So what does this graph look like? Well, for anyone who's taken Math 30, you know it kind of goes up and is in a wave like this. If we're looking at just the first, say the first 15 degrees here, then this part is a very straight line. and it's essentially a linear relationship. Once we get into angles that are bigger than 15 degrees, well, then you can see that it sort of comes off of this line. So you don't have to really know too much about why it works. Just remember that this only works for small amplitudes. And we call this the small angle approximation, that sine of an angle is sort of a straight line for small angles. And so keep this little equation here in mind. You don't have to, this one is not found on a formula sheet or anything. But just keep in mind, just like when we were talking about ramps, it's a very similar way of working out what this force is here. So quick example, and then we'll call that an end of this video. We'll say how far from vertical has a 100-gram pendulum. Well, the bob of the pendulum is 100 grams. Pulled from equilibrium. If the restoring force is 0.17 newtons. And we want to know how far has it been pulled in degrees. So we've got a pendulum. It's been pulled to the side by some angle. And it's got a force here that's causing it to return to equilibrium. This force is 0.17 newtons. And the mass of this pendulum is 100 grams, or 0.100 kilograms. And we want to know what the angle is. So remember, we said our restoring force, which is this force here, was equal to the force of gravity multiplied by sine of theta. So really what we want to do is we want to isolate for theta here. So we can do that. Restoring force divided by the force of gravity is equal to sine of the angle. So that means that the angle itself is going to be equal to the arc sine of the restoring force divided by the force of gravity. The force of gravity in this case is, of course, just going to be mass times acceleration due to gravity. We're talking about on Earth. In this unit, you'll see we are going to talk about some cases where we're not on Earth, but for now, we are on Earth. So just the arc sine of 0.17 newtons divided by 0.1 kilograms multiplied by 9.81 meters per second squared. And this gives us an angle, if we plug this into our calculator, work it out, of 10 degrees. So really just in this section, just get comfortable working with springs, figuring out what the restoring force is but for a spring, figure out what the restoring force is for a pendulum. And then we're going to talk about a little bit more next class about what happens once you actually let go. Instead of just holding it there, just pulling it to the side, what happens when we let go. So that's next time.